Welcome, my dear student. So in this lecture series, I am going to show you some of the application of impulse momentum relation to solve the problem in physics. Okay. So whenever the impulse momentum relations are to be applied, that means I cannot do the conservation of momentum. So conservation of momentum just before and just after collision is not applicable whenever the force is impulsive in nature. Okay. Let us say start with the first situation where there is a bullet of 0.5 kg is moving with the speed of 100 meter per second and it's get embedded inside this block. So once it hits, it will penetrate the block and it stick to the block. So you are asked to calculate the distance traveled by the block before coming to rest. Now in this situation, what is happening? So there is an impulsive force that is acting on the 0.5 kg after the impact. So let us say this is the bullet. So on that bullet there is a force. Let us say R is the force acting, and there is same force acting on the block also. Okay. So if I consider the entire system of bullet and block system, then the net impulsive force becomes cancelled. So under that situation, I can apply the conservation of linear momentum for the two systems together. Okay, that means taking the bullet and the block together. Let us say after the impact, just after impact, the block is moving with the velocity v0. So conservation of momentum is being applied just before and just after the collision. So what we can write, the initial momentum should be equal to final momentum here. Okay, though the impulsive force is there, but as a whole, impulsive cancels out, so I can write this. So what is the initial momentum? Initial momentum is equals to 0.5 into 100. 0.5 into 100 is the initial momentum of the bullet, and ultimately 2 plus 0.5 kg, that is the total mass, is moving with the velocity v0. Okay, so from that, what I can get, the value of v0 is equals to 20 meter per second. 20 meter per second. So that means after the impact is over, now the bullet block system is moving with a velocity of 20 meter per second. Now you are asked to calculate the distance traveled by the block before coming to rest. So after the impact, so block and bullet system, that is 2.5 kg mass, is moving with a velocity v0. And after that, some point of distance traveled, so it comes to at rest. Why? Because here the velocity becomes 0, because in this surface the friction is there. So friction is acting in this direction. What is the friction force? That should be equal to mu times mg. Friction force is mu times mg. So I can apply the work energy conservation theorem. So for that, what you write? The work done by the friction. So I am writing work done by friction should be equal to final kinetic energy plus final potential energy minus initial kinetic energy plus initial potential energy. So I am writing the work energy conservation. So work done by the friction is how much? Minus mu mg into s. That is, the s is the displacement. Let us say the distance traveled by the bullet block system is s. So mu mg into s with the negative sign is the work done by the friction. And final kinetic energy is 0 because it comes to at rest. Now there is no change in the potential energy because I am saying this is our reference line. So both the block and the bullet are on the same reference line. So potential energy is not changed. And that is initial kinetic energy. That means half m into v0 square. Okay, so negative cancels out. So m also cancels out. So ultimately s is equals to v0 square by 2 mu g. That is the displacement travel. Okay, so v0 square is 20 into 20. By 2 into 0.5 into 10. So becomes 10. So 400 by 10 means 40 meter. So 40 meter is the displacement of the bullet block system after it comes to rest. Okay. So there is an impulsive force, but that impulsive force is not taken into account by considering the entire bullet block system. Okay. Now moving on to the next situation. Now the same block is connected with the spring. Same block is connected with the spring, having the spring constant is given and mu is given, and the bullet is hitting the block. Now again the impulsive force comes in the picture, but what we can do that, again if I do the same analysis for the bullet block system combined together, okay, just before and just after. So just before and just after, if I say just after, the bullet is moving with the same speed v0. And ultimately the bullet block system will move in this direction with, let us say, v0. Okay, if I do the same analysis, so ultimately what I am getting, that initial momentum should be equal to final momentum just before and just after collision. Again I can write, because There is no impulsive force acting. Net impulsive force becomes 0. So what we can write that 0.5 into 100 is the initial momentum. That should be equal to final momentum. So final momentum should be equal to how much? 4.5 into V naught. Okay. So from that, what I'm getting, that V naught number is equals to 50 divided by 4.5. That means it is equals to how much? 11.11 meter per second. Okay, this is the velocity with which the block is moving. Now, ultimately, it comes to rest. Find the maximum compression. So, maximum compression takes place when the spring, let us say this is the compression of the spring. Ultimately, the bullet is, or the block is coming at rest. So, V equals to 0. At this position, let us say the compression of the spring has to be calculated. Now, so displacement of this system is, let us say, X. So, X is the compression. X is the compression. So, what is this X? This X is the X number. So, X is the compression, or I can say X is the displacement before the block comes to rest. So, again, the work done by the friction. So, again, the friction is there. So, I can write the work done by the friction, that should be equal to kinetic energy final plus potential energy final minus kinetic energy initial plus potential energy initial. Okay. So, what is the work done by the friction? That is again minus mu mg into X. Kinetic energy final is 0. Potential energy is there because the spring has compressed by X distance. So, half K S square is the spring potential energy minus half m V naught square is the initial kinetic energy. Okay. So, once I solve this equation, that will give the value of X. Okay. So, this is a quadratic equation. You can solve it to get the value of X. So, this is how you have to approach the problem so that you can find what is the maximum compression, or we can say that this is the displacement of the bullet block system before it comes to rest. Okay. Now, what is happening if the bullet is hitting the same block with an inclined direction? So, in this situation, what is happening? The initial momentum corresponds to 10 meter per second. Now, finally, so initial momentum has two components. If I take the initial momentum, so let us say Pi. So, what is Pi? Pi is 10 kg meter per second. Okay, kg meter per second. So, this is the initial momentum. So, Pi has two components. One is along X. So, that is a Pi initial along X. So, that should be how much? That should be 8. And similarly, Pi initial momentum along Y is also there. That is our 6. Okay, because now the bullet is hitting the block at some inclined point. So, that means here what is happening? The impulse is coming on the bullet. So, if I say this is the impulse direction on the bullet R. So, R has two components. One is the vertical component and another is the horizontal component. So, this vertical component of R is giving the N, that is the normal component, normal force acting on the 4 kg block is impulse. Because of that, now the friction becomes impulsive. In the earlier two situations, friction is not impulsive. So, now the friction becomes impulsive. Why? Because the vertical component of R is coming into the picture. So, if I say the normal component Ny dt is the impulse on this block. So, implication of Ny dt is the impulse. That should be equal to P final minus P initial. Okay. Now, what is P final? P final of the bullet is equal to 0. I am applying this equation on the bullet itself. So, P final, so along the Y direction. So, along the Y direction, this is 0 minus or minus 6. Okay. So, from that, what I am getting, that Ny dt with implication is equal to plus 6. Okay, there is an impulse along this Y direction. Now, this Ny dt number will be the friction. So, friction is what? Friction is basically or mu into Ny. That means now the friction becomes impulsive. Now, this friction will increase the velocity. Okay. So, once I apply the concept of this friction, which is impulsive in nature, that is creating the change in speed. Okay. So, the bullet is making contact with 10 to the power minus 4 second. So, that means the delta T number is known. So, I can calculate the Ny number from that. Okay. So, once I got the Ny number, I can calculate the friction. So, because of this friction, there is an increase in velocity of the 4 kg block. Okay, 4 kg block. So, you can do this calculation to calculate what is the final momentum of the 4 kg. Because initial momentum of the 4 kg is 0. There is no change in the initial momentum of the 4 kg. So, only thing the momentum has been changed along the X direction because of this friction. Now, friction is acting in this direction. Okay. Because the normal component of R is on this block is in this direction. Impulsive force. So, that component, X component is pushing this in this direction. and y component is vertical. Okay, because of that the friction is coming into the picture, and that will give the impulse, which is that because of the 4 kg gain the speed. Okay, so you can solve this. Now let us say, now these 2 kg or 4 kg blocks are connected by the string. Now you are asked to calculate the final velocity of the system. So once they are connected with the string and the bullet is being again hit by this 4 kg block, okay, so in this situation, now the tension becomes impulsive. Now this tension, this T is impulsive. Because of that, their T is also impulsive. So I cannot write the momentum conservation directly over here. So I have to write the separate 3 equation for the first bullet, then 4 kg, then 2 kg. So what I am going to write? The impulse momentum relation. That is integration of F dt. That should be equal to final momentum minus initial momentum. This is the equation that I am going to write for 3 bodies. So let us say I first write the equation for the 4 kg block. For the 4 kg block, so there is an impulse that is acting on this bullet as, let us say, this R number. So if I take the right hand side is a positive, so for the 4 kg block, so net impulsive force is R minus T dt. Integration of that should be equal to P final minus P initial. So after the impact, let us say the 4 kg is moving with the velocity v. So final momentum is 4v. Initial momentum is 0. So this is the first equation. Similarly, I can apply the same impulse momentum equation on the bullet itself. So on the bullet, R is acting in the left direction. So it should be minus R dt should be equals to P final. So bullet is moving finally with velocity 0.5 v naught, 0.5 v, and initial momentum is 0.5 into 20 minus 0.5 into 20. This is the bullet equation. Similarly, on the 2 kg block, impulse is forward direction. So integration of T dt. That should be equals to P final minus P initial. So after the impact is over, so 2 kg will also now move with velocity v. So it should be equals to 2v minus 0. Okay. So first write the 3 basic equation for this. So this is equation number 1, equation number 2, and equation number 3. Now once I add all these 3 equations, then what happens? This minus that is plus R will cancel out. This minus T plus T will cancel out. So on the left hand side, that number will be equals to 0. That should be equals to how much? 4v plus 2v plus 0.5. Okay. So 4 plus 2 plus 0.5 v, that should be equals to our 10. So that is v should be equals to 10 by 6.5. That will be your answer. That is the final common velocity with which the entire system is moving. So now, if I want to apply the conservation of momentum, so if you clearly follow the diagram, what I can say that for the entire bullet block and the 2 blocks and the bullet, so for the entire system, if you take this as a system, so net force is 0. Why? Because this P and that T will cancel out. So this R acting on the 4 kg block and there is another R which is acting on the bullet will also cancel out. So net force on the system is 0, and that means I can apply the conservation of linear momentum for this as a whole for the entire system. So for the entire system, if I write Pi equals to P final, initial momentum is how much? 0.5 into 20. This is the initial momentum. And finally, all the blocks, 4 plus 2 plus 0.5, all are moving with the same speed v. So then again I am getting the value as 10 divided by 6.5. Okay. So if you do this careful analysis, then only you can get the idea that for this system also I can apply the conservation of linear momentum if you take as a system of whole. Okay. So moving on to the next situation, let us say now these 2 blocks are connected with the spring, not by a string. Okay. Now once they are connected with the spring, now the spring force is not impulsive. Now spring force is not impulsive, it is non-impulsive force. Non-impulsive force. So non-impulsive force means now you can do the energy balance. So once the bullet is being hit on the 4 kg block, so what is happening? So initial momentum should be equal to final momentum. I can directly apply this. So what is the initial momentum? Initial momentum is 0.5 into 20. That is the initial momentum. Finally, all the blocks that is 4 kg and 0.5 kg are moving with the speed v. So I am applying the conservation of momentum between this bullet and the 4 kg, not the entire system. So initially the bullet has momentum with this much. So once the bullet is being hit by the 4 kg block, so now the momentum has been changed. That is equal to 4.5 into v naught. Let us say they are moving with the velocity v naught. Okay. Now the system the 4 kg starts to move with the velocity v naught. So from that, what is the value of v naught? That v naught equals to, I am getting as 20 by 9. 20 by 9 meter per second. So this is the velocity of the system. It is the 4 kg is moving. Now in the same system, once the bullet is being hit, now we may be asked what is the final compression, maximum compression. Now what is there? So 2 kg is initially at rest. So 2 kg is initially at rest. Now the problem is like this way. So there are two block system where this 2 kg and 4 kg are there. Not 4 kg, it is 4.5 kg because 0.5 is already there inside that. It is 4.5 kg. So this 4.5 kg starts to move in this direction just with v naught. Now you are asked to calculate the maximum compression. Now for this you have to apply the concept of reduced mass. That means from the center of mass reference frame you have to take care about the kinetic energy. So I will prepare another video for dealing with this type of concept where the two block particle system are there, and for that particular system you can apply the concept of reduced mass so that the problem will be much easier. Okay. So initially in this situation you are asked to calculate the velocities. The velocity should be equal to 20 by 9. Now keep in mind that in this situation where the blocks are connected to the spring, now the force is not impulsive in nature. Okay. So that's why you can apply directly conservation momentum. Now let us say there is another situation where there are two blocks are connected with the pulley block system and the bullet is being fired. It will hit this mass and ultimately all the systems are moving the same velocity. You are asked to calculate the velocity of the system. Now again there is an impulsive force acting on the bullet, and because of that the tension becomes also impulsive here. Okay. Now tension on this end is in this direction. This is impulsive. Tension on this block is T over this direction. So that is also impulsive. Okay. And on this bullet there is one impulsive force. Let us say R is acting over here, and on this block the R is acting downward. Okay. So all are impulsive force. Now we have to write separately for three systems. So for this bullet, let us say this is the bullet. So for this bullet, R, the impulsive force is acting upward. For this mkg, there is one impulsive force T is upward and R is acting downward. And for there is another mkg block is there. For that, T is acting upward. So after the impact is over, let us say this block is moving with the velocity v. This block is also moving with velocity v. And this block is moving upward with the velocity v. Okay. Now we can write the separate three equation. So for this bullet, what I can write, that is if I take R is the upward direction is positive, so integration of R dt, that should be equal to final momentum. So final momentum downward is negative. Downward is negative, so minus mv minus initial momentum. Initial momentum is also downward, minus m into v naught. Okay. So in this equation, I am taking the upward is positive. So based on that, I can write this equation. So it becomes mv with a minus sign plus mv naught. Okay, this is the first equation. Now moving on to the next system, that is the block. So if I take the upward as positive, so t minus r. The second equation is integration of t minus r dt. That should be equal to final momentum. So final momentum is moving downward, means minus m into v. Okay, minus m into v. And initially there is at rest, so there is no initial momentum. Now finally for the third equation, so if I take upward is positive, so it should be integration of t dt. That should be equal to final momentum. So final momentum is upward, so it is plus mv. Okay, so these are the three equations. Now you have to add and subtract carefully so that I can get the final answer. So if I add 1 and 2, so then R will cancel out. With that equation, if I subtract the 3, so then P will also cancel out. So what I am doing, so I am adding 1 and 2 and subtracting from 3. Okay, so left hand side becomes 0. Left hand side becomes 0. So add 1 and 2 means minus 2mv plus mv naught. Subtract with the third equation, that is minus mv, that should be equal to 0. So that means I am getting 3mv should be equal to m into v naught, or what I can say, v should be equal to v naught by. Okay, that is the final answer. So that means the entire system is now moving downward. So this block is moving downward with the velocity of v naught by 3, and this block is moving upward with the same speed, that is v naught by 3. That will be your answer. Okay. Now you can do it by conservation of momentum also without writing this three equation. So what I can do, so if I take the entire system, so this R and R will cancel out. Okay. And that T will not cancel out. So for that, what you do, so once you are getting the idea that 1 plus 2 plus 3, that gives 0, that means you can do the conservation of momentum. But here, 1 plus 2 minus 3 will give the value of 0, that means you cannot directly apply the conservation of linear momentum. So for that, I have to go for the impulse momentum relation. So every problem can be dealt with this linear momentum conservation, cannot be dealt with this linear momentum conservation equation. So, but all the problems can be dealt with this impulse momentum relation. That's why this equation is most powerful equation. But whether we should apply that or not, that depends on the situation. If I able to apply the conservation of linear momentum, then I don't go for this impulse relation. Okay, but impulse relation will always hold. Impulse relation will always hold whether the force is 0 or not. Now, moving on to the next situation, let us say there are two balls are attached with the thread and which is initially loose. The distance between the, let us say this is the A ball, this is the B ball. They are kept in a horizontal plane. So this is on the horizontal plane. Now they are connected with the string. Initially the string is loose condition. Now we throw the ball B with the speed of V0. Ultimately, once the ball B will reach over here, so it will, now the string will become taut. Now it has been observed, it has been given that at an angle 37 degrees the string is tight. So now the string will give it impulse in this direction T. Similarly, this will also get the impulse T in this direction. Okay. So along the direction of impulse, you have to apply the conservation of momentum. So correspondingly, initially, the block B is thrown with the velocity V0. That means at this position, it is also going with velocity V0. So what is the initial momentum along the impulse direction? That is the component of impulse. That is the component of velocity. So that should be equal to 4 V0 by 5. And here this component is 3 V0 by 5. Okay. So since this component is perpendicular to the direction of the impulse, so after the string is being taut, so there is no change in the 3 V0 by 5. So let us say after the string is being taut, the B ball is moving in this direction with a velocity V. Similarly, the ball A will also move in this direction V. Okay, so this V corresponds to the final momentum. So once I apply the impulse momentum relation for, let us say, for the ball A, I'm taking downward as positive. So I can write integration of T dt equals to final momentum, that is M into V minus 0. Similarly, for the ball B, now the impulse is minus T dt. That should be equal to final momentum. So what is final momentum? Mv minus initial momentum. So minus initial momentum is minus 4 m v0 by 5. Okay. Now if I add these two numbers, so now the integration part will be cancelled out. So on the left hand side, again I am getting 0. That should be equal to 2 mv minus 4 m v0 by 5. So now this m will cancel out. So I am left with v should be equal to 2 v0 by 5. So this is the final velocity of the ball A and B together. Okay. So if I say this is the final velocity V of the ball A and B, so that is along the direction of the impulse. So what is the net velocity of the ball B? So net velocity of ball B should be for the ball B, there is one velocity 2 V0 by 5 in this direction, and that velocity remains same 3 V0 by 5. That is already there. Okay, there is no change in 3 V0 by 5. So that is the two different velocities on the ball B, and ball A, for the ball A only one single velocity is there, that is along the impulse direction, that is equals to 2 V0 by 5. Okay, so that will be your answer. So these are the some of the examples where I am going to apply the impulse momentum relation. Okay, so hope you understand this. Thanks for watching my video. If you like it, please subscribe my channel.